Good day, everyone. Welcome to the subject Advanced Differential Equation. I am Joe Victor Liepa from Pasig National High School, and with me is Sir Ivan Planto, who was assigned in module writing. Today, I will discuss the second order partial differential equation. At the end of this presentation, we will be able to first define second order partial differential equation. Second, classify second-order partial differential equation. And third, solve some examples of second-order partial differential equation. So what is a second-order partial differential equation? A partial differential equation, or briefly a PDE, is a mathematical equation that involves two or more independent variables, an unknown function, and partial derivatives of the unknown function with respect to the independent variables. The order of a partial differential equation is the order of the highest derivative involved. So, when we say second order partial differential equation, this means that we have the second derivative as the highest derivative of the partial differential equation. A solution to a partial differential equation is a function that solves the equation, or in other words, turns it into an identity when substituted into the equation. A solution is called general if it contains all particular solutions of the equation concerned. Classification of second-order linear partial differential equation. Consider the generic form of a second-order partial differential equation in two variables with constant coefficients, a times u sub xx plus b times u sub xy plus c times u sub yy plus d times u sub x plus e times u sub y plus f times u is equal to g of xy. For the equation to be the second order, a, b, and c cannot all be 0. Define its discriminant to be b squared minus 4ac. The properties and behavior of its solution are largely dependent of its type as classified below. The linear partial differential equation of the second order in two independent variables is of the form a of xy del squared u over del x squared plus b of xy del squared u over del x del y plus c of xy del squared u over del y squared plus f of x, y, u, del u over del x, del u over del y is equal to 0. If b squared minus 4ac is greater than 0, then the equation is called hyperbolic. The wave equation is one such example. If b squared minus 4ac equals 0, then the equation is called parabolic. The heat conduction equation is one such example. And if b squared minus 4ac is less than 0, then the equation is called elliptic. And the Laplace equation is one such example. In general, elliptic equations describe processes in equilibrium, while the hyperbolic and parabolic equations model processes which involve overtime. Consider one-dimensional damp wave equation. 9 del squared u over del x squared is equal to del squared u over del y squared plus 6 del u over del y. For the solution, it can be written as 9 del squared u over del x squared minus del squared u over del y squared minus 6 del u over del y equals 0. It has coefficients a equals 9, b equals 0, and c equals -1. So where did we get this 9, 0, and -1? So if we are going to look back on our general form, we can see here that a is equal to 9, b is 0, meaning we don't have any coefficient for b of xy, and c is equal to -1. Now, if we are going to look at the discriminant, b squared minus 4ac equals 0, so this will now become, or by substitution, this will become 0 squared minus 4 times 9 times -1, or that is equal to 36. And since 36 is greater than 0, or the discriminant is greater than 0, therefore, the equation is hyperbolic. Example number 2. Consider the equation del squared u over del x squared plus 4 del squared u over del x del y plus 4 del squared u over del y squared minus del u over del x plus 2 del u over del y equals 0. So again, if you are going to check for a, b, and c, we can see here that a is equal to 1, or the coefficient of del squared u over del x squared is 1. Then b is 4, and for c is also 4. So for the solution, then we can say a is 1, b is 4, and also c is 4. Substitute this to b squared minus 4ac, so we can have 4 squared minus 4 times 1 times 4. Or this becomes 16 minus 16, or equal to 0. And since the discriminant b is equal to 0, therefore, the equation is parabolic. Example number 3. Consider x squared del squared u over del x squared plus the quantity 1 minus y squared del squared u over del y squared equals 0, where x is greater than negative infinity but less than positive infinity, and y is greater than -1 but less than +1. Now again, if we are going to check on the general form, a here is equal to x squared, b is none or 0, and we have here c is a quantity 1 minus y squared. So for the solution, first, we have the coefficients a equals x squared, b equals 0, and c equals 1 minus y squared. By substituting this on b squared minus 4ac, we have 0 squared minus 4 times the quantity x squared times the quantity 1 minus y squared. And as a result, the product is 4x squared times the quantity y squared minus 1. Now notice that for all x between negative infinity and positive infinity, 4x squared will become positive. And for all y between negative 1 and positive 1, y squared will become less than 1, or that is negative. Hence, the discriminant is less than 0. So therefore, the equation is elliptic. And for example number 4, consider the equation a quantity 1 plus x squared del squared u over del x squared plus the quantity 5 plus 2x squared del squared u over del x del t plus the quantity 4 plus x squared del squared u over del t squared equals 0. So again, if we are going to check from the general equation, a here is equal to a quantity 1 plus x squared, b is equal to the quantity 5 plus 2x squared, and c is equal to the quantity 4 plus x squared. Now for the solution, the coefficients a is equal to 1 plus x squared, b is equal to 5 plus 2x squared, and c is equal to 4 plus x squared. Substituting this on our b squared minus 4ac, so we have a quantity 5 plus 2x squared squared minus 4 times the quantity 1 plus x squared times the quantity 4 plus x squared. Now squaring the first quantity, we got 25 plus 20x squared plus 4x to the fourth. And getting the product of the second quantity, we can have negative 16 or minus 16, then minus 20x squared, then minus 4x to the fourth. And if we are going to look at the equation, we can cancel some terms here which are considered additive inverses, such as 20x squared and negative 20x squared. And we have also 4x squared and negative 4x squared, or 4x to the fourth rather. So, as a result, we can have 9. Now, since the discriminant is 9, which is greater than 0, so therefore, the equation is considered to be hyperbolic. So these are some examples on how to classify or identify the second order partial differential equations. Now let us come on solving second order linear partial differential equations. Just like we were able to determine higher order derivatives of function in one variable, we can also determine higher order partial derivatives of function in two or more variables. Since there are two first order partial derivatives of functions of two variables, there will be four second order partial derivatives of functions of two variables. The notation for second order partial derivatives is very important. Now we have to take note of these important notations for the second order partial differential equation. So when we have del over del x of del u over del x, this is also the same as del squared u over del x squared, which is also equivalent to u sub xx of xy, or which is also the same as u sub xx or z sub xx, or that is also the same as f sub xx. So when we say f sub xx, this means we can differentiate 2 times with respect to x. So for del over del y of del u over del y, so this is the same as del squared u over del y squared, which is also similar to u sub yy of xy, which is also equal to u sub yy or z sub yy or f sub yy. And this means that we can differentiate 2 times with respect to y. Also, for del over del y of del u over del x is just the same as del squared u over del y del x, or this is also the same as u sub xy of xy, which is also equal to u sub xy or z sub xy or f sub xy. Or this means we can differentiate with respect to x and then y. So that means we have to differentiate first in terms of x, and after that, we have to differentiate again in terms of y. Now another one is del over del x of del u over del y is just the same as del squared u over del x del y, which is also equal to u sub yx of xy, or the same as u sub yx, or also z sub yx, or also f sub yx. Or this means we have to differentiate with respect to y first and then x. Now let us come to the geometric interpretation of second order partial differential equation. Now, if f sub xx is greater than 0, then f of xy is concave up in the x direction. So concave up. So that means that is opening upward. If f sub yy is greater than 0, then f of xy or f of xy is concave up in the y direction, or that means that is opening upward in terms of y direction. So mixed partials tells us how a partial in one variable is changing in the direction of the other. And f sub xy also tells us how the rate of change of f of xy in the x direction is changing as we move in the y direction. Now let us come on solving second order partial differential equations. So determine the second order partial derivative of f of xy is equal to 2x to the fourth minus 5x cubed y cubed minus y to the fourth. So first, we have to find the first derivative with respect to x. So the first derivative of f of xy with respect to x for the first term, for 2x to the fourth, we have 8x cubed. For negative 5x cubed y cubed, we can have negative 15x squared y cubed. And for negative y to the fourth, we have 0. So therefore, the first derivative with respect to x is 8x cubed minus 15x squared y cubed. Now another one, we're going to find the first derivative of f of xy with respect to y. So looking at the first term, 2x to the fourth, the derivative of this with respect to y is 0 because there is no y variable. And for negative 5x cubed y cubed, the derivative of this with respect to y is negative 15x cubed y squared. So we just consider x cubed as a constant. And for the derivative of negative y to the fourth is negative 4y cubed. So therefore, the first derivative with respect to y is 15x cubed y squared minus 4y cubed. For the second derivative of the function f of xy with respect to x, so we simply get this, or we simply find the derivative from the first derivative with respect to x also. So for the derivative of 8x cubed, we can have 24x squared. And for the derivative of negative 15x squared y cubed, considering y cubed as a constant, so we can have negative 30x y cubed. So therefore, the second derivative of the function with respect to x is 24x squared minus 30xy cubed. For the second derivative of the function with respect to y, so likewise with the second derivative of the function with respect to y, we're going to find, or we are going to base this from the first derivative of the function with respect to y. So for the derivative of 15 or negative 15x cubed y squared, granting or considering x cubed as a constant, we can have negative 30 x cubed y. And the derivative of negative 4 y cubed with respect to y will become negative 12 y squared. And therefore, the second derivative of the function with respect to y is negative 30 x cubed y minus 12 y squared. Now, for the partial derivatives, so uh, we're going to have first the partial derivative of the function with respect to x first and then y. Or this is for d squared of f over dx dy. So this means we have to find first the derivative of the function with respect to x. Then after that, we have to find the derivative again of the function with respect to y. As a result of a derivative of a function with respect to x. So, if we are going to look at the df over dx, this is already the first derivative of a function with respect to x. So for the derivative of the function with respect to y, we will simply find the derivative of this, no, with respect to y. So for 8x cubed, the derivative of this with respect to y is 0 because there is no y variable. And for negative 15x squared y cubed, considering x squared as a constant, this will become negative 45x squared y squared. And therefore, the second order partial derivative of the function with respect to x and y will become negative 45x squared y squared. And also, for the second order partial derivative of the function with respect to x, to y and x, uh, again, we are going to base this from the derivative of the function with respect to y. So, if we are going to have the derivative of 15 x cubed y squared, getting the derivative of this with respect to x now, so considering y squared as a function or as a constant, this will become negative 45 x squared y squared. And for negative 4x or 4y cubed, the derivative of this with respect to x is 0 because there is no variable x involved. And so therefore, the second order partial derivative of the function with respect to y and x is now equal to negative 45 x squared y squared. So notice that the resulting derivatives or the resulting second order partial derivatives of the function are equal with each other. So for d squared of f over dx dy is equal to negative 45 x squared y squared, and also for d squared of f over dx dy, which is also equal to negative 45 x squared y squared. So looking at the solution, we have noticed that the mixed partials d squared f over dx dy and d squared f over dx dy have the same answer, which is negative 45 x squared y squared. So that is true because of mixed partial derivatives. Given f of xy with d squared f over dx dy and d squared f over dy dx are continuous over this region, then d squared f over dx dy is equal to d squared f over dy dx. Or f of xy is equal to f of yx. Let us have another example. Example number 2. Determine the second order partial derivative of f of xy is equal to xe raised to xy squared. For the solution, first, we are going to find the derivative or the first derivative of the function with respect to x. So using the derivative of the product and also a chain rule. So consider the technique u dv plus v du, considering x as u and e raised to xy squared as our v. So we simply copy x first, then multiply to the derivative of e raised to xy squared, which is e raised to xy squared times y squared. Then plus copy e raised to xy squared times the derivative of x, which is 1. So as what we can see, we have a common factor of e raised to xy squared. So we can rewrite and simplify this as e raised to xy squared times the quantity xy squared plus 1. So that is now our first derivative with respect to x. So next to that, we're going to find the second derivative of the function based on the result of our first derivative of the function with respect to x. So again, we're going to copy e raised to xy squared times the derivative of xy squared plus 1, which is y squared, plus copy again xy squared plus 1 times the derivative of e raised to xy squared, and which is e raised to xy squared times y squared. Now, if we're going to simplify, we can have 2y squared e raised to xy squared plus xy to the fourth times e raised to xy squared. So next to this, we're going to find the first derivative of the function with respect to y. So in this case, we're going to consider all x as our constant. So again, we're going to use the derivative of the product. So in this case, we're going to consider again x as u and then e raised to xy squared as our v. So finding the derivative of this with respect to y, we come up with x times the quantity e raised to xy squared times 2xy. And simplifying this, we can have 2x squared y times e raised to xy squared. And finding the second derivative of this now with respect to y again, we can have 2x squared y times the quantity e raised to xy squared times 2xy, which is by chain rule. Then plus e raised to xy squared. And simplifying this, we come up with 4x cubed y squared e or times e raised to xy squared plus 2x squared times e raised to xy squared. Since the first derivative of the function with respect to x is already given by e raised to xy squared times a quantity xy squared plus 1, and the first derivative of the function with respect to y is also given by 2x squared y times e raised to xy squared. Then, for the second derivative of the function with respect to x first, and then followed by y, so this is equal to e raised to xy squared times 2xy plus the quantity xy squared plus 1 times e raised to xy squared times 2xy. And if we are going to simplify this, we come up with 4x y times e raised to xy squared plus 2x squared y cubed times e raised to xy squared. So this is now the second order or the second partial differentiation of the function with respect to x first, then followed by y. Now, for the second differentiation of a function with respect to y first, then followed by x, so we come up with 2x squared y times e raised to xy squared times y squared plus e raised to xy squared times 4xy. And simplifying this, we come up with 4x y times e raised to xy squared plus 2x squared y cubed times e raised to xy squared. So again, as what we have noticed, the second derivative of the function with respect to x then followed by y is just the same with the second derivative of the function with respect to, or the second partial derivative of the function with respect to y then followed by x. Thus, d squared f over dx dy is equal to d squared of f over dy dx. To summarize what we have learned from this topic, first, a partial differential equation or PDE is an equation containing an unknown function of two or more variables and its partial derivatives with respect to these variables. Second, the second-order partial differential equation can be classified as hyperbolic if b squared minus 4ac is greater than 0, parabolic if b squared minus 4ac is equal to 0, and elliptic if b squared minus 4ac is less than 0. And in second-order partial differential equation, given that pf of xy with df over dx dy and df over dy dx are continuous over a disk region, then d squared of f over dx dy is equal to d squared of f over dy dx. Presenting here is our references for this topic and also the URL of online materials used in this presentation. That ends our presentation for today, and may the good Lord bless us all. Thank you very much for watching.